I worked in GE lighting for 30 years. I worked in measurements a lot, and one of my frustrations is, okay, what are the measurements on these devices? So through a contract, through the Maryland, I was able to get funding so we could take a look at that. So I'm gonna describe the spectral and angular output of the Ushio's 4-tube krypton chloride excimer lamp, which is used in a lot of devices. And I want to understand then from the role of the spectral filter plays, and I want to understand what the total power is. Now, to me, the critical measurement of the device is what's the total power in the UV that you're interested in. If you want to know how much dosing is, that's the number. Radiance doesn't matter. Not that much. It matters in terms of safety, but it doesn't matter in terms of dosing. So this is the device. Actually, it's PJ Piper's Krypton 36 lamp, and then also with the diffuser. And so that's the unit I'm gonna have measured. Let's see. Okay. I guess I can look here. I used Light Lab International to make the measurements. By the way, there are not a lot of labs who do good UV measurements. And this is one. There's a few other ones. As a side job, I audit laboratories for lighting measurements. So I know all the labs out there in the United States and Europe and China for that matter. So, and I wanted them to do goniometric measurements from which I get total power, and spectral measurements. And kudos to Gigahertz Optics. They use their devices. And by the way, there are not a whole lot of companies out there that provide good measurement instrumentation that can be used. So they're one. Let's see, where do I point this? Okay, what I want to do then is to make goniometric measurements of the pieces, so to speak. I take the filter out, so I can see what the effect just of the lamps are as received with the filter, and then add a diffuser. And I want to accompany the goniometric measurements, which are angular based, with spectral measurements for the same set of characteristics. Okay, so what I'm going to do, and rather quickly, I'm going to run through a lot of graphs. I'm going to show 3 slides of the unit without the filter, so the goniometric measurements in various angles. And by the way, these are not fully symmetric. You have 4 lamps, okay? So how you look at it as in angularly changes very much. And then I want to look at the spectral measurements at every 10-degree increments, both at 0 and 90 degrees. And I want to compare then the spectral sum of the measurements with the gonio measurements. So here you see the measurements as a function of angle. And you notice that even without a filter, it kind of dies at about 60 degrees. It's not a cosine. There are a couple of reasons for that. One is that the discharge looking in one direction is all in the center of the tube, not much at the ends. And then the other end, the lamps get hidden by themselves because they're in a row. So you lose actually more faster than a cosine. And you notice the angular difference. I don't think I want to point out that's too important. Here's the spectral data every 10 degrees. I don't show 10, 20 degrees because it's they're all clustered there, even 30 degrees. And then you see, but as you drop down, by the time you get to 60 degrees, you're pretty well, not much left. But notice that there is a significant, obviously, amount of radiation. If you want to talk about ozone, this is the portion that counts. You also see that there's a long tail here. This is, of course, why this creates the problems with or with the long wavelength. So we want to take those out, and that's what the filter does. All right. The spectral data, and I was very pleased. The points are the sum of the data, spectral data over the UVC region versus the angular data. And you see how well the points match the line? Okay, so that says, okay, the calibration of both devices give the same numbers. That's very important. So very pleased, and so the lab did a really nice job based on that. Okay, next, let's take a look at the as received with the filter. Same set of data. Okay, well, you notice the long wavelength's gone, filter does its job, but it does something else, and this is not so good. Okay, 30 degrees. Well, what happened between 30 and 40 degrees? Notice that the edge of the filter is moving this way, and it's cutting out the 222. Because the band edge on the filter is at about 230, as you move toward angle, that band edge moves. By the time you get to 40 degrees, there's nothing left. So the filter creates a problem. It takes the power out of the system above 40 degrees. Well, in terms of the power in the space above 40 degrees is where most of the power is. So you lose a lot of power. And by the time, so this is a big issue. Okay, and here is the comparison of the two without the filter and with the filter. And you see you have a loss even at the beginning, the filter. This is mostly due to taking out the long wavelength. So that's expected. But here, this is due to the loss due to the filter itself. It took the power out, it cut it out. It's no longer available. Okay. I think I must be, let's see. Okay. Let me mention one other thing. Notice this is without a filter, and this is with a filter, the red line, and then with a diffuser. You've taken this out, which is very good. You've actually, the filter lowers the radiation at UV. It actually, filter is removing this. So that helps the ozone problem. So this is very good. And it's an order of magnitude of 200. So it makes a big difference. And then the diffuser, but notice that the diffuser is, well, and this is at 0 degrees. And then I want to do it at 40 degrees. Okay, so now we're looking, not normally, but we're looking at 40 degrees. You notice this is the area where, whoops, the filter now, you see you've lost, at 0 degrees, these were basically the same, but now they're not. So, but the filter seems to have almost no radiation down below 210. And well, part of it is it probably does, but it's very hard to read because it's in the noise region of the measurement. The filter, in addition, this is the diffuser. If the diffuser was having an output of a cosine, it would follow the blue line. It doesn't. It falls off by 70 degrees. Notice again, the power, when you look at power over a sphere, it's multiplied by the sine of the angle, or the cosine, 1 minus the cosine of the angle. So at 90 degrees, you have multiplied by 1. At 0, you multiply by 0. So the amount of power is a lot of it is lost there. So we have a lot of power loss. Okay, and I ran through this very quickly. Here's the data then of all 3 devices. This is the goniometric data falling off here. That's because of the edges. The lamps are downset. You have this loss due to the filter. And now, oh, and by the way, now I'm summing only over up to 230. I'm discounting all the radiation above that. So it's not this line that I've taken away the high wavelength region. I get 200 milliwatts there. I get 101. I lost half the power by putting the filter on it. Half the power below 230. Okay, what does that mean? Well, the filter means that if I could have the filtered light at the power here, I'd need half as many lamps. And notice here, when I put the diffuser on, I lost half the power again, almost. So by putting a diffuser on, I need two lamps to get the same room dose. So my point and my argument is that, guys, take a look at the design. I think we can improve a lot. A lot of it is the way it's stacked. And Holger, I don't know on the filter whether you have a chance, but I would move the edge of the filter back 5 nanometers. You're going to get. You could. I think this number could go to 150. And I'm not sure on the diffuser. I think it's partly a stack, but partly it's the filter. The filter is only putting radiation in up to 40 degrees. You're trying to diffuse it, but the diffuser has nothing to work with that past 40 degrees. So this is, again, the diffuser has a problem because of the filter. So these are the things that I learned from the measurements. And so in summary, the filter works as expected. It removes emission below 220, which is also good, reduces ozone generation. But because of the filter action with angle, you lose the line after 30 degrees, basically. And so the efficiency there you see is 0.9 watts with the filter. The watts in was 1145. Okay, with the diffuser, diffuser effectively spreads emission as it's expected to do. You'd reduce the normal intensity by a factor of 5, which of course is what you want to do. You don't want to have the direct hit, you want to spread it out. But you also lose a factor of 2 and you get further ozone reduction. So it's only 0.48% with the diffuser. Now, the other thing is the pre-publication from Jose Jimenez's data, which I thought was very interesting. I can now compare my measured power with their measurements of CBR4 photolysis rate, and I get a really interesting comparison. I get below 230, I got 0.2 watts without a filter, 0.1 without or with the filter, and 0.054. Here's the photolysis rates. You basically say it's the same number. It says photolysis rate is a good way of looking at this if you want to compare it. On the other hand, the ozone generation, okay, it was 100 here, so there was a factor of 5. This is due to the reduction in the radiation below I'd say below 220, mostly below 210. And then the diffuser had another reduction of a 2.5, which I'm not quite sure. I would rather not have that there. I would rather do this. That's my conclusion, and I will acknowledge the work we have. The University of Maryland, they provided funding for us to do NALMCO and also to get these measurements, which I would not have done. One final comment, and I think Cameron is here. Given the issues we have with Kenny Wood, what radiation is between 200 and 190? Nobody can do that yet. We need those measurements. They're complicated, and I think Cameron's going to try to take a look at that. We need calibration, we need the detectors. Also, the problem is the quartz lamps transmission becomes probably very opaque by 190. But what's there? So that's a recommendation in addition. But I think you can, these measurements I wanted to have and publish so that they are available for everybody, because Holger's lamps are used a lot, and with the filter.
Thank you very much, Rolf. Again, I think in the interest of time,
Okay.
we'll move on to the next presentation, but please grab Rolf at lunch.